It came from the direction of Vega. That is one of the first things astronomers figured out once they started tracing its path backward through the solar system. The object had entered from the general direction of Vega, one of the brightest stars in the northern sky, a star that humans have been looking at and naming and navigating by for thousands of years. It had not come from Vega specifically. The timing did not work out. It would have left the vicinity of Vega hundreds of thousands of years before Vega was even in that part of the sky. But it came from that direction, from somewhere out there among the stars, from a point of origin we have never identified and may never identify, traveling through the dark between stellar systems for an unknown length of time before. In the autumn of 2017, it fell into the gravity well of our Sun, swung around it in a hyperbolic arc, and began heading back out into interstellar space. We had, at that point, never detected a single object that had originated outside our solar system. We had theorized that such objects should exist, drifting between the stars. We had built no specific systems for finding them. And we found this one almost by accident, late, when it was already leaving, giving us only a few weeks to study it before it moved beyond the reach of our best telescopes. We named it Oumuamua. In Hawaiian, the name means something like a scout, or a messenger, or the first of a distant place arriving here. The people who chose the name were being poetic. They may have been more right than they knew. To understand why Oumuamua became one of the most debated objects in the history of astronomy, why it broke out of the science community and into the broader culture, why it is still being argued about in journals and on stages and in books years after the object itself is gone, you have to understand what astronomers expected the first interstellar visitor to look like, and then understand, piece by piece, how thoroughly this object failed to match those expectations. Start with what we knew before Oumuamua. The idea that interstellar objects, rocks, ice, debris, should drift through space between star systems is not controversial. When solar systems form, the process is violent and wasteful. A young star with its protoplanetary disk is a chaotic environment. Planetesimals colliding, giant planets migrating, gravitational interactions flinging material around at high velocities. A lot of this material ends up in stable orbits within the solar system. Some of it gets ejected. The gravitational slingshot effects of the forming giant planets can accelerate small bodies to escape velocity, launching them out of the solar system entirely and into interstellar space. This happens in every planetary system. The galaxy should be full of interstellar wanderers, rocks and ice and debris from billions of planetary systems, drifting through the dark on trajectories shaped by whatever ejection event sent them flying. The estimated population of such objects in our galaxy runs into the quintillions. There should be so many of them that any given region of space, including the space around our Sun, should be regularly transited by them. The question was never whether interstellar objects existed. The question was whether we could detect them. Detection is hard. An interstellar object moving through the inner solar system is small, dark, fast, and present for only a brief period before it swings around the Sun and heads back out. The window for observation is narrow. The object needs to be both close enough and bright enough to appear in survey images, and the survey needs to be pointed at the right part of the sky at the right time. For decades, no interstellar object was found, not because they were not there, but because the surveys were not sensitive or wide-field enough to catch them in the short time they were detectable. The survey that found Oumuamua was the Pan-STARRS telescope on Haleakala in Hawaii. Pan-STARRS, the Panoramic Survey Telescope and Rapid Response System, is a wide-field telescope system designed specifically to survey the sky repeatedly, looking for moving objects, near-Earth asteroids, comets, anything that changes position between one observation and the next. On October 19, 2017, a Pan-STARRS image showed a point of light that had not been there the night before. The object was moving fast, much faster than any known solar system body at that distance from the Sun. The initial reduction of its orbit immediately showed something extraordinary. The trajectory was hyperbolic, not just slightly hyperbolic, as some comets from the outer Oort cloud can be when their orbits are perturbed, deeply hyperbolic, with an eccentricity of 1.2, meaning the object was moving far faster than the Sun's escape velocity, moving on a path that could only be explained if the object had arrived at our solar system already moving at interstellar velocities. It had not originated here, it had come from somewhere else. It was the first confirmed interstellar object ever detected. The discovery paper was written in hours. The astronomical community erupted. Telescopes around the world turned to look at it. Every major observatory that could point in its direction did so. The Hubble Space Telescope was requested. Ground-based facilities in Hawaii, Chile, the Canary Islands, Arizona, all of them gathered observations as fast as they could because the object was already past perihelion, already heading outward, already getting fainter every night. The observing window was closing. In the few weeks they had, astronomers managed to gather enough data to determine several things about the object's physical properties. And those properties were where the strangeness began. The first weird thing was the shape. As astronomers watched Oumuamua over multiple nights, they noticed that its brightness was varying dramatically, not the gentle sinusoidal variation of a slowly tumbling sphere, but a sharp, large amplitude variation that repeated approximately every 8 hours. The object was brightening and dimming by a factor of 10 over this cycle, which is an extraordinary range. For context, most asteroids and comets vary in brightness by a factor of 2 to 3 as they rotate, because even irregular objects are not that much brighter face-on than edge-on. A brightness variation of a factor of 10 implies a shape that is extremely elongated, an object that is much longer than it is wide, presenting a large cross-section to sunlight when oriented one way and a tiny cross-section when oriented the other way. When astronomers ran the numbers, they came up with an aspect ratio, the ratio of the object's length to its width, of approximately 10 to 1. Some estimates pushed it even higher. This was an object that was 10 times longer than it was wide, maybe more. If it was cigar-shaped, it was the most extremely cigar-shaped natural object ever observed in the solar system. If it was flat, like a pancake or a disk, the same brightness variation could be produced with a similar extreme aspect ratio. No known solar system asteroid or comet had been observed with an aspect ratio remotely close to this. The most elongated natural objects in our solar system have aspect ratios of maybe 3 to 1, and those are considered unusually elongated. 10 to 1, possibly higher, was genuinely unprecedented. Astronomers immediately noted that extreme elongation is unusual for natural objects, which tend to round out over time through collisions and rotational effects. But unusual is not impossible, and there were proposed natural mechanisms by which a rock could end up in this shape. Tidal forces during a close planetary encounter, for instance, can stretch and elongate objects under the right conditions. So the extreme elongation was noted, discussed, written about, and provisionally filed under very weird but possibly natural. The second weird thing was the color. Spectroscopic observations of Oumuamua showed that it was reddish, not dramatically red, but distinctly so, more red than most solar system asteroids. This reddish color is consistent with the surface chemistry expected of material that has been exposed to cosmic radiation over long periods of time. The kind of radiation processing that happens when a small body drifts through interstellar space for millions or billions of years. This was actually somewhat comforting to astronomers, because it was consistent with the object being old interstellar material, and it fit the expected surface characteristics of a body that had been floating between the stars for a very long time. The color, in isolation, was not obviously problematic. The third weird thing, and the one that made the object genuinely impossible to explain in conventional terms, was what happened when astronomers tracked its trajectory with extreme precision. As Oumuamua moved outward from the Sun after perihelion, its path was tracked with the greatest accuracy the available instruments could provide. And when the observed trajectory was compared to the predicted trajectory based on purely gravitational forces, the Sun's gravity and the gravitational influence of the planets, all of which were known with extraordinary precision, there was a discrepancy. Oumuamua was not where it was supposed to be. It was being pushed away from the Sun by some force in addition to gravity. The deviation from the gravitational trajectory was small but statistically significant, growing larger over time as the object receded, and pointing consistently outward, away from the Sun, in the direction that radiation pressure from sunlight acts. This kind of non-gravitational acceleration is not, in itself, unprecedented. Comets experience it all the time. When sunlight heats a comet's icy surface, gases and dust are ejected, a process called outgassing, and the reaction force from this jet of material acts like a gentle rocket thruster on the comet's trajectory, nudging it off the purely gravitational path. This cometary outgassing is well understood and routinely incorporated into trajectory calculations for known comets. When astronomers saw the non-gravitational acceleration of Oumuamua, their first instinct was cometary. It must be outgassing. Problem solved. Except it was not solved, Because when astronomers looked carefully at Oumuamua with every available instrument, they could find no evidence of outgassing at all. Comets that are actively outgassing are surrounded by a coma, a cloud of gas and dust that is visible in images and detectable through spectroscopy. Oumuamua had no coma, none was detected. Upper limits on the amount of gas that could be present without being detected were established, and those upper limits were far too low to explain the observed acceleration through conventional cometary outgassing. If Oumuamua were outgassing at the level required to produce the measured acceleration, the gas should have been easily detectable. It was not there. The object was accelerating away from the sun at a rate that could not be explained by gravity and could not be explained by outgassing and could not be explained by any other conventional mechanism that astronomers could identify. The acceleration was real, the data was good, and no known physics accounted for it. This is the point at which a specific person enters the story, and the story of Oumuamua becomes not just a mystery about an object, but a human story about what it means to follow an argument to its conclusion, when the conclusion is something that your entire professional culture is trained to avoid saying. Avi Loeb is an astrophysicist. At the time of Oumuamua's discovery, he was the chair of the astronomy department at Harvard University, one of the most prestigious positions in the entire field of astronomy, in the most famous university in the world. He had published hundreds of papers across a wide range of astrophysical topics. He was not a crank, he was not a fringe figure. He was, by any reasonable measure, one of the most credentialed and academically established astronomers on the planet. And when Oumuamua's non-gravitational acceleration was confirmed, Avi Loeb began working through the implications with a collaborator, a Harvard postdoctoral researcher named Smal Bialy, and arrived at a conclusion that he then did something remarkable with. He published it. The paper was titled, in the understated language of academic astronomy, "Could Solar Radiation Pressure Explain Oumuamua's Peculiar Acceleration?" It appeared in the astrophysical journal Letters in November 2018, about a year after the discovery. The argument in the paper was straightforward, but its conclusion was extraordinary. Loeb and Bialy noted that solar radiation pressure, the gentle push that sunlight exerts on any object, could in principle explain the observed non-gravitational acceleration if the object had an extremely unusual shape. Specifically, if Oumuamua were not a thick cigar or a chunky rock but an extremely thin, flat sheet, something like a sail or a wafer, very wide and very thin, then its ratio of surface area to mass would be high enough for solar radiation pressure to produce the observed push. The thickness required if the object had a density similar to rocks would be less than a millimeter. A sheet of solid material roughly the size of a football field and less than a millimeter thick. No natural process was known to produce objects of this shape. The paper said so explicitly. It then noted that such a shape was consistent with a manufactured object, specifically with something like a light sail, the kind of thin, large, low-mass sail that physicists and engineers have actually proposed building for interstellar spacecraft. A light sail works by using the pressure of starlight as a propellant. In the absence of any rocket fuel, a thin enough sail with a large enough area can be pushed by starlight alone across interstellar distances. Breakthrough Starshot, a project announced in 2016 and backed by physicist Stephen Hawking and entrepreneur Yuri Milner, was developing exactly this concept for a proposed mission to Alpha Centauri. The technology was not science fiction, it was engineering. And if you built such a sail from a distant star system and sent it in the direction of our solar system, it would behave when it arrived, somewhat like Oumuamua behaved. Loeb and Bialy did not say Oumuamua was definitely an alien light sail. They said it was one hypothesis, alongside natural explanations, that was consistent with the observations, and that it deserved consideration. The paper ended with the suggestion that the possibility of an artificial origin should not be dismissed and should motivate further study. The reaction from the astronomical community was swift, and it was not warm. The criticism came from multiple directions. Some colleagues argued that the thin sheet hypothesis was physically implausible, that no natural or artificial process could produce an object of those dimensions that could survive the stresses of interstellar travel and the gravitational and tidal forces of swinging around a star at perihelion. Others argued that Loeb and Bialy had jumped to an exotic conclusion before exhausting natural explanations, that the absence of detected outgassing did not rule out unconventional forms of outgassing that might not produce the expected coma. Still others argued, more bluntly, that proposing an artificial origin for an astronomical object without overwhelming evidence was irresponsible speculation that would generate public confusion and harm the credibility of the field. The Harvard Astronomy Department did not formally distance itself from Loeb's paper, but the informal signals from colleagues were unmistakable. He was being told, in the language scientists use with each other when they disapprove, that he had overstepped. Loeb did not back down. He wrote more papers, he gave more interviews, he began a book, published in 2021, titled Extraterrestrial: The First Sign of Intelligent Life Beyond Earth, in which he laid out his reasoning at length for a general audience. The book was a bestseller. It put him in front of audiences far beyond the astronomy community, and it made his argument in a way that was accessible and, he believed, intellectually honest. Here is the data. Here are the alternative explanations. Here are the problems with each of them. Here is why I think the artificial hypothesis deserves serious consideration rather than reflexive dismissal. He became a polarizing figure in astronomy, celebrated by some for his willingness to say what others thought but would not say, criticized by many others for promoting what they saw as an unfounded and irresponsible claim. The specific counter-arguments that emerged from the scientific community are worth examining carefully because they reveal the genuine difficulty of evaluating evidence for something as unprecedented as an interstellar artificial object. The most prominent alternative explanation that emerged after Loeb and Bialy's paper was the hydrogen iceberg hypothesis. Two astronomers, Daryl Seligman and Gregory Laughlin, proposed that Oumuamua might be composed primarily of molecular hydrogen ice, a form of solid hydrogen that theoretically could exist in the very cold conditions of dense interstellar molecular clouds. If the object were a chunk of hydrogen ice, it would sublimate, turn directly from solid to gas as it heated up near the sun. This outgassing would produce the observed non-gravitational acceleration without producing the observable coma, because hydrogen gas is nearly invisible to the spectroscopic techniques used to detect the more typical cometary gases like water vapor, carbon monoxide, and carbon dioxide. Hydrogen is so transparent at most relevant wavelengths that an outgassing hydrogen iceberg might accelerate without any detectable outgassing signature. The hydrogen iceberg hypothesis was elegant. It was a natural explanation that avoided the need for anything exotic, and it was embraced by much of the community as the most plausible resolution to the Oumuamua problem, which is what this had come to be called. But the hypothesis had problems of its own. Hydrogen icebergs are extremely fragile. The same sublimation process that would produce the outgassing would also cause the object to shrink dramatically over time, and the object would need to have been quite large when it entered the solar system to have survived the transit. Moreover, hydrogen ice requires very cold formation conditions that are only met in the densest, coldest cores of molecular clouds. Whether objects could actually form in those conditions and then be ejected into interstellar space as hydrogen icebergs was far from certain. And some subsequent analyses found serious problems with the numbers. The object would have to have been sublimating at a rate that should have been detectable even for hydrogen, and the formation pathway remained theoretically murky. The hydrogen iceberg hypothesis solved some problems and created others, and it was not accepted as definitively as the enthusiasm of its initial reception suggested. Another hypothesis that emerged was nitrogen ice. Loeb's Harvard colleague Avi Mandel and separately researchers Jackson and Desch proposed that Oumuamua could be a fragment of a Pluto-like body from another planetary system, a chunk of nitrogen ice, similar to the material on Pluto's surface, ejected during a collision. Nitrogen ice, like hydrogen ice, would sublimate near the sun and produce an invisible outgassing signal, and nitrogen ice-rich bodies are thought to be common in the outer regions of planetary systems. The nitrogen ice hypothesis was considered more physically plausible than hydrogen ice by many researchers, and it could also potentially explain the extreme flat shape if the object had been sheared off the surface of a larger body by a collision. Loeb engaged with the nitrogen ice hypothesis directly and found problems with it. The amount of nitrogen ice that would need to have been ejected to produce the population of objects that the Oumuamua detection rate implied was far more than plausible planetary formation models would predict, but the hypothesis remains in the literature as a candidate. The problem, underlying all of these competing explanations, is that Oumuamua is gone. It is not coming back. By the time the scientific community had fully processed its anomalous properties and developed the full range of hypotheses to explain them, the object was already beyond the reach of even the most powerful telescopes. There is no follow-up observation possible. There is no additional data to be gathered. Every conclusion anyone draws has to rest on the observations made in those few frantic weeks in late 2017, which were good observations but were rushed and incomplete and did not include some of the measurements that would have been most useful for distinguishing between hypotheses, particularly long baseline measurements that would have better constrained the non-gravitational acceleration, and very deep spectroscopic observations that might have detected or placed stronger limits on various outgassing products. Astronomers were working with what they had, which was always less than they needed. This is one of the most painful aspects of the Oumuamua story, the one that the scientists who worked on it return to most often when they talk about it in reflective moments. We were not ready. We had never detected an interstellar object before. We had no protocol. We had no dedicated telescope time on standby for exactly this situation. When the object was confirmed as interstellar, the scramble to get observations was improvised and heroic, and ultimately insufficient. If there had been a telescope with a dedicated program for monitoring fast-moving objects near the Sun, if there had been a protocol for immediately triggering large aperture spectroscopy on any newly discovered hyperbolic object, if the detection had happened even 2 weeks earlier, the dataset on Oumuamua would be dramatically richer than it is. As it stands, the dataset is tantalizing and permanently incomplete, which is the worst possible combination for resolving a mystery. The astronomical community responded to this failure of preparation by developing better protocols. The discovery of the second confirmed interstellar object, 2I Borisov, detected in 2019, benefited from the lessons of Oumuamua. Borisov was discovered much earlier in its trajectory, giving observers months rather than weeks to study it. And Borisov was far more cooperative as an object. It showed a clear coma, clear outgassing of water and carbon monoxide, a more conventional cometary composition, and a shape that was consistent with a normal comet nucleus. It was essentially a perfectly ordinary comet from another star system. It was fascinating for being the first definitive interstellar comet ever observed, but it was not anomalous. It fit. It made sense. It was the first interstellar object that astronomy was prepared to understand, and it understood it without great difficulty. The contrast with Oumuamua was stark and in some ways made Oumuamua seem more anomalous in retrospect, not less. If Borisov showed what an interstellar comet looks like, and it looked like a comet, then Oumuamua, which looked nothing like a comet and produced none of the signatures Borisov produced, was not a comet. This has been one of Loeb's persistent arguments. Borisov is the control case. Borisov is what interstellar rocky or icy material looks like when it passes through the inner solar system. Oumuamua looked nothing like Borisov, therefore Oumuamua was not simply an interstellar rock or comet. Whatever it was different. Whether different means exotic natural object of a type we have never encountered, or something manufactured, is where the debate lies. But the Borisov comparison strengthened the case that Oumuamua was genuinely anomalous, rather than just an ordinary object whose anomalous properties were artifacts of poor data. There are people who have thought about the Oumuamua problem in a different way, and their perspective adds another dimension to the story. SETI researchers, the people who spend their professional lives thinking about what evidence of extraterrestrial intelligence might look like and how we would recognize it, have mostly been cautious about Oumuamua. The SETI Institute, for example, did look at Oumuamua with the Allen Telescope Array and found no radio emission, no narrowband signal, no evidence of active transmission. This was noted and incorporated. If Oumuamua were an artificial object, it was not actively broadcasting. But the absence of radio emission does not rule out an artificial object any more than the absence of radio emission from a passing satellite rules out the existence of satellites. An artificial light sail coasting through a stellar system with no propulsion active and no active communication system would not be expected to broadcast anything detectable. The SETI community's caution has been partly methodological. SETI researchers are trained to demand very high standards of evidence before claiming detection of extraterrestrial intelligence, having lived through decades of false alarms and public misinterpretation, and partly institutional. The lesson of Oumuamua for SETI was that it provided a test case for thinking about what evidence of an artificial object might look like. Not a signal, not a message, not something that announces itself, but an object that passes through and whose artificiality, if present, is encoded in its physical properties rather than its transmissions. This is a profoundly different kind of evidence than the kind SETI has historically been designed to find, and grappling with it forced some productive thinking about expanding the conceptual framework of the search. Loeb has since founded a program he calls the Galileo Project, explicitly designed to look for evidence of extraterrestrial technology in the data of large sky surveys. The project has deployed instruments, published papers, and gathered a team of researchers. It has, at the time of this writing, not detected anything that its members consider confirmed evidence of extraterrestrial technology, but it is operational and ongoing. Loeb has described the project as the scientific response to the epistemological situation that Oumuamua created. If anomalous objects can pass through our solar system and we are not looking for them, we will not find them even if they are there. Looking systematically is the only way to find out whether they are. The broader scientific community has had mixed reactions to the Galileo Project, as they have had mixed reactions to Loeb throughout the Oumuamua controversy. Some researchers respect the scientific seriousness with which he approaches the question and appreciate that he has used his platform to argue for rigorous observational programs rather than simply speculating. Others continue to feel that his public promotion of the alien hypothesis is disproportionate to the evidence and has, at the margin, associated the scientific establishment with a claim that most of its members do not believe is well supported. This tension is real and uncomfortable and does not have a clean resolution. Science is not supposed to be decided by popularity. The history of science is full of cases where the consensus was wrong and the dissenter was right. But it also does not progress well when individuals with large platforms consistently advocate for extraordinary conclusions that their peers find unwarranted by the evidence. What is clear, stripped of the controversy and the personalities, is that the data on Oumuamua is genuinely difficult to explain with conventional physics and is not obviously explained by any of the natural hypotheses that have been proposed. Every proposed natural explanation has problems. This does not mean any of them are wrong. Having problems is not the same as being false, and sometimes problems with a hypothesis are resolvable with better data or better models. But the situation honestly described is that we detected an object with an unprecedented combination of properties: extreme elongation, no detectable coma, non-gravitational acceleration of uncertain cause, and an interstellar trajectory from an unidentified source. And we have not been able to explain it fully with any known natural process. That is where the data leaves us. It does not prove alien technology. It does not rule out alien technology. It rules out some natural explanations clearly and rules out others weakly, and the space of genuinely viable explanations remains frustratingly large. There is something about the human dimension of this story that the purely scientific account misses, and it matters. Avi Loeb is, whatever you think of his specific conclusions, a person who looked at the data and decided to say what the data suggested to him, in full awareness that doing so would cost him professionally and socially. His colleagues did not exactly shun him. Harvard is not the kind of place where you get fired for publishing a controversial paper, but the informal currency of scientific reputation is real and was affected. The knowing glances at conferences, the papers that pointedly did not cite his work, the colleagues who made their disagreement clear in public comments. He absorbed all of this and kept going because he believed his argument was correct and that intellectual honesty required stating it. You can disagree with the argument and still admire the stubbornness. There is something in the scientific enterprise that requires exactly this kind of stubbornness: the willingness to follow evidence to unpopular places and hold the position under social pressure. And it appears relatively rarely because the incentive structure of academic science punishes it. Meanwhile, the volunteers and graduate students and postdocs who did the actual work of observing Oumuamua in those frantic weeks, who called in favors to get telescope time, who stayed up through the night collecting photons from a rapidly fading point of light, who ran the trajectory calculations and the spectral analyses under intense time pressure, mostly went on to other projects, because that is what scientists do. The object was gone, the papers were written, the data was public. The question of what Oumuamua actually was went into the category of things that science cannot currently answer, which is a larger category than the popular image of science suggests. Not everything gets solved. Not every mystery yields. There is a postscript to this story that is both humbling and galvanizing. Astronomers have calculated that objects like Oumuamua, interstellar visitors on hyperbolic trajectories, should be relatively common, given what we know about how planetary systems form and eject material. The reason we had not detected one before 2017 was not that they are rare, but that our surveys were not sensitive or wide-field enough to catch them in the narrow window of detectability. The Vera Rubin Observatory's Legacy Survey of Space and Time, which began full operations in the mid-2020s, is the game-changer here. It is a telescope with an enormous field of view and a camera with billions of pixels, designed to image the entire visible sky every few nights in multiple wavelengths. Its sensitivity to faint, fast-moving objects is dramatically greater than any previous survey facility. Estimates suggest that LSST will detect one or more new interstellar objects per year, possibly many more. We went from 0 confirmed interstellar objects before 2017 to 1 a year, roughly, going forward. Within a decade, we may have detected dozens of them. Most of these will probably look like Borisov, normal cometary bodies from other planetary systems, weird only in their interstellar origin. But some of them, statistically, may be unusual. Some may be anomalous. Some may look like Oumuamua. And when they are detected, we will be more ready than we were in 2017. There are now protocols for rapid follow-up of hyperbolic objects. There are now discussion groups organized and ready to coordinate observations. There is now a community of researchers who have thought carefully about what we would want to measure on an interstellar interloper and how to get those measurements quickly. The next Oumuamua, if there is one, will be studied better than the first, and if it accelerates without outgassing, and if it is shaped like something no natural object should be shaped like, and if all the natural explanations have the same problems they had before, we will be better equipped to face that situation with open eyes and an honest accounting of what the data is and is not telling us. That is the lesson of Oumuamua, more than any specific scientific result. Not that we found an alien probe. Maybe we did, maybe we did not. The evidence does not compel a conclusion, but that the universe is capable of showing us something we have never seen before, something that resists every framework we bring to it, and that our job when that happens is not to force it into a familiar category, but to sit with the genuine strangeness, argue carefully and honestly about what it means, and keep our eyes open for the next one. The object is gone. It crossed our solar system in the span of a few months, a vanishing moment by the standards of the universe, and whatever it was, whatever it came from, whatever made it the shape it was and pushed it away from the sun the way it was pushed, it is now somewhere in the dark between the stars, moving at interstellar velocity towards some future encounter with some other star, in some other era, that no one alive today will ever know about. It passed through. We noticed. We scrambled. We argued. We still do not know. It came from the direction of Vega. It left in the direction of Pegasus. In between, for a few weeks, it was close enough to be the subject of more scientific attention per unit time than perhaps any other object in the history of astronomy. We pointed every instrument we had at it, stayed up through night after night collecting data, argued about it in papers and at conferences and in private conversations at exactly the level of intensity that the situation deserved, and we could not figure out what it was. One of the most scientifically accomplished people in his field looked at all of it and said, "I think it might have been made." His colleagues mostly said, "We don't think that's right." And the object flew on into the dark, indifferent to all of it, keeping it secret, gone. The universe sent us something and we did not understand it. That has happened before and will happen again. What matters is that we looked. What matters is that we argued honestly about what we saw. What matters is that we built better protocols so that the next time something comes from out there and passes through, we will see it sooner and study it longer and leave fewer questions on the table. What matters is that we are paying attention. Oumuamua, the scout, the first of a distant place arriving here. The name was chosen to fit the occasion, and it does. Something came from far away and passed through and left. Whether it knew we were here, whether anything in the universe that produced it has ever wondered what might be watching from this small warm planet as it went by, we cannot say. We do not know what it was. We may never know. But we saw it. Out of all the moments in the history of this solar system, in all the billions of years before any eyes existed here to look up, it passed through in the exact window of time when we had built instruments sensitive enough to notice. We noticed. That is everything. That is the whole story. We noticed, and we argued about it honestly, and we kept our eyes open for whatever comes next.